Hello, this is Jacob Briggs, and I am here to talk about the graph um, project. I did the quote unquote option 3 that was talked about in the one uh, on Thursday, last Thursday, where we kind of write our own. So I used the STL to create one, and I still did like everything that was for option 2. So, yeah. So, I'm going to start off by saying graphs are confusing, and I'm glad that there were plenty of online resources to use to help me get a better understanding on how to do different things. So I understand most of it, but there's some of it that it's like, this is still like magic to me, and I understand the idea, but I don't know how it's doing the things that it does. So let's get into it. So first, we make a data structure to have our graph edges, which it connects two vertexes, which we make down further in the down here. We have our number of nodes, which is our also our vertexes. Um, and we make 20, and then we also make 20 edges right here. Anyways, let's go back up, and then we have our graph, and we make our adjacently. I've been struggling to say this every single time I've said it out loud. Adjacency list. There we go. That's the one. Um, so we construct a vector of vectors to represent an adjacency list. And then we store. Uh, this is for the topological sorting. Uh, to get the in-degree, all the in degree stuff is for topological sorting. Um, and then we have our graph constructor, um, where we resize the vector to n elements, which is down below. We make our all of our vectors, and then we initialize our in degree to use for topological. Um, and then we add edges for directed graph, so that's also used down below. This is all stuff that we just do later. Um, this is our print um, representation function of the graph for each integer, for each integer in the graph. So it goes from 0 all the way to when it ends, which will be, since it's 20, it'll technically be 19. So 0 to 19 it goes through, and it prints our vertex number right here. So it'll say this is 0, and then 1, and then 2, and it'll come here, and then it'll print all the neighboring vertices of vertex I. So what it'll do is it'll go into the list, and it'll say, hey, what's attached to this little boy right here? And if it is attached, then it displays that, and then it gets out of there and says, all right, that's it for this one. Now go on to the next one. Do it for that one. Um, and I can talk about this stuff in just a little bit. I'm going to show that we create 20 nodes, and then here we just make a whole bunch of edges, and we construct our graph with these edges and this many nodes, and then we're going to print the graph, and I can do that right now and show that off. So here we go. We have all of these connections, made some that don't have any, made one with many, just to show off that all of that works. And all of these connections were made right in here. Um, so that's just our main graph, how we do all of this. um, so if we come, okay, what's next? The one that is uncommented is depth first search. So let's come up here to the depth first. There's a lot of stuff in here that I try to talk too fast and I can't say it. Depth first search, which depth first search and breadth, I don't know if I'm pronouncing that right, first search do the same thing just differently. This one uses queues and this one typically uses stacks, but the example I looked at didn't put them into a stack. It just kind of went through it. So let's look at this one first. So we have this one called discovered. We make a little thing here called discovered, and it's a boolean for our vectors. So what it'll do is it'll make sure that we don't do something twice. So what it does is when you get to a node, you'll say, hey, you found this one, now you can't do it again, so that you don't go multiple times and put like 15, since it has so many connections, you don't do 15 so many times. Um, and then it prints the current node, um, so it prints out which one we're on, and then it puts a space so we can do that for every edge and have them all in one line. It'll go through the list in our graph, excuse me, um, and if it's not discovered, then it calls itself to do this on here. But if it is discovered, then it's just like, okay, we done this one already. We don't need to do this again. So let's pull this up and show that off. So here we see that we start off good and then we like go all over the place as it goes through everything. Um, and everything, I believe everything is on here, no matter what. 9, 10, 11, 12, 13, 14. Yeah, everything's on here. And then let's just talk about, before we like switch everything around and show this one off, or show off that it gives the same thing, because they use some of the same stuff down here. So I have one commented out and the other one isn't. We can look at the breadth one in action later and just talk about it. So this one uses the same sort of discovered method, but this one, instead of just like saying put it in there, this one creates a queue, um, and it does the same sort of thing. Once it finds one, it says put that in there. Just put it right in there. And then it does the same sort of thing down here, where it'll run through each one here, um, or really what it does is it says, hey, wait, keep doing this stuff until it's empty. And what it'll do is it pops whatever's on the front and it displays what's next, if that makes sense. It probably does. um, and how it does that is it does like exactly the same thing as this, pretty much, except instead of um, just outing it, it pushes it onto the queue, and then the queue pops it after, and then displays it, or displays the next. And we can look at that in a second because it gives the same thing. It's just two ways of doing the same thing. And then here is the real magical one that I sort of understand. I understand what the topological sort it does. What the topological sort does is it starts at what has no connections, and then it starts to move down the tree, or the graph, so to speak, and eventually just shows in order like how from the top, so what has no connections, and it runs down from there, and it's like these are the order in which things connect from there. So it starts at whatever is like, there's nothing on me. Um, and then it keeps going down from there. So this is all magic. um, I went through I, this is the one that is like the hardest one to understand for me, like how the code itself works. I just kind of worked through with the example, and it ended up working. So I'm going to go through it right now and hope that I can explain it good. So we have our topological sort on our graph. We find our graph, we have our integer, we have an L and an N. We set all of our nodes with no incoming edges. So that's like, I believe no incoming edges is all of our stuff that doesn't have anything connecting back to it. So, for example, the one that I found here is 18. Nothing here has 18 on it. So when we go through it, 18 starts at the top. And then everything else comes from there. And just to show that it does work, if when I first did it, I forgot to put one thing in, and it immediately hit me with this. Um, so, um, yes. So it starts off with our boy that has nothing that goes onto it. And from there, it's just like, oh, we're going to find everything else. I'm not sure exactly how it all works. Let's see if I can pull. I think this is the topological. Yes, it is. So, yeah. So it's the things that have the least amount of incoming things on it. So not just, it doesn't go in order, my bad. It does not go from order like 7 to 1. It's everything that doesn't have anything attached to it comes first, and then um, it goes from there, and then it shows all the other connected stuff. So that's why it would go 18, 17, because I don't think anything is connected to 17 either. Let's look through here. No. Um, but 7 is connected at 17. So that's why I would go 18, 17, and then 7. And then it just goes on from there from various different connections. It's really, really weird. I also could not figure out what a cycle meant. I believe that's for a different kind of graph, or it might not be at all, and I just haven't understood everything there is to know about graphs, and I'm sure there's a lot I don't, because this is all new to me. Everything else that we talked about, I had like some sort of prior knowledge on, or have worked with something that's kind of like it. This is the first thing where it's like, I have no idea what this is, and I'm going to try and make it and understand it. And I did with everything. Well, most everything. This is the only thing that's like still fighting me back. I'm glad that I had um, online resources to figure out how to do this. I was looking at everything else, and this seemed like something that would be fun to implement. Um, so the code in here, we set all of our nodes with incoming edges. We talked about that. And then while S, so S would be everything that has no incoming edges. So while that's not empty, so while there's still things with no edges, um, we remove a node N from S and add N, so a node N, add N to the tail of L, and then down here is for, I believe this is for the whole list of n. Um, yeah, so this, I think this is how we find out what we want to insert into S. Um, so what this does is it finds everything in here, and it says if you don't have anything, then you're actually going to go into S, and this is what you do for S. So this is how you find your first ones. And then if graph has edges, then graph has at least one cycle, and then this just does a for loop. And if in degree, which is up here, um, and this is a destination thing, it increases it by one for an edge. Um, so each edge that something has, it gets plus one. So I believe that's what that would mean. That's usually what that would mean. Um, yeah, I'm sorry. I really wanted to try and understand this better, but all I understand is what it's doing, and the code is still a little bit mind-boggling. Uh, so, oh wait, I forgot to show, um, I forgot to show, uh, the breadth first searching working before I completely ended everything, and show that it does essentially, oh, wait a minute. I think it puts it in a different order actually. It was not doing that just a second ago, but I think I might have changed, um, I guess that would make sense because, uh, queues, are queues first in, first out? Queue priority. This isn't what I meant. Queue versus stack. That's what I would want. Hold on. I'm sorry. I just want to figure this out. Oh, it was right there. Um, queue first in, first out, stack last in, first out. Um, I'm either going crazy or this changed orders and I didn't realize it. It might have been that one. Hold on. I'm sorry. I feel really, really bad right now for this video being so long. Oh, okay. They were in the they were in the same order. Oh my goodness. I was just because I saw 18 last and then this one was 18 first, so I got everything or 18 and 17, 18, 17. So everything got thrown off because of that. I am so sorry. How do you redo? I can't redo. Anyways, let me just do this again. So we can look at it. Now that I figured out my little dilemma there. So yeah, it essentially does the same thing since I'm not actually putting DFS into um, a stack structure. I'm just C-outing it uh, with how my example showed me. Um, they do the same thing. They just do it in different sorts of ways. This one I think is a little neater because you put it into a queue instead of just throwing it out there like this one. But this one, in the way that it's written as of right now, is probably a little faster because you don't, and better for memory because you don't create this queue. Um, and then again, this one, we go down um, from the ones that have no connections, or no edges, not no connections, no incoming edges, so nothing is trying to go to it. Nothing has 18 or 17 here. Um, and then from there it just keeps going down until it hits everything at least once. Um, yeah, thank you. I wish I could have done a video where I had a better understanding, but this is the stage of understanding that I'm in right at. Thank you again.